We're going to finish up the lecture on stoichiometry with percent yield. Percent yield is a very easy concept because it's one that you're familiar with when it comes to calculating the percentage that you receive on your test scores and on your lab scores. It's very similar because it's important in a lab that we know how efficient the outcome is of a product. So it's an indicator to check the efficiency of a lab or industrial reaction. Theoretical yield is the maximum amount of a given product that can be formed when the limiting reactant is completely consumed. And let me take this opportunity just to say, once again, that all along we have been calculating theoretical yield. That's what our outcomes have always been. Theoretically, that's how much we should make in product. The actual yield is less, and it's going to be less than the theoretical, and this is the amount that you're going to have calculated from a lab experiment. So when you're doing problems, the actual yield will always be given to you. All right. So the actual yield divided by the theoretical yield times 100% is your percent yield. And remember, actual will be given to you because that would be something that you did in the lab and something that you couldn't carry out in a problem that you're working out right in front of you from your textbook. And theoretical yield is the amount that we've always calculated before. How much product would we end up with? All right, let's look at an example. It says find the percent yield of product if 1.5 grams of SO3 is produced from 1 gram of oxygen gas, and you have excess sulfur in the reaction. And it wants the percent yield. This number that it gives us here is an actual yield. So in order to come up with, and remember, let's do our equation, it's going to be actual divided by theoretical times 100. So this actual yield is right here. So we have to calculate the theoretical yield, which is something we've all done all along. So let's remember that it's grams to moles, mole to mole ratio, and moles back to grams again. So I have to change grams of oxygen to moles. So I know that 1 gram times 1 mole is going to be 32 grams because it's O2. So 16 times 2 is 32. So I take 1 and divide it by 32, and I get 0.03125 moles of O2. Now in this case, I don't have to figure the limiting reactant because it tells us that the sulfur is in excess, so I have way more than I need. A possible scenario would be for them to ask you to calculate the limiting reactant and then go ahead and finish the problem like it states. So we have 0.0312 moles of oxygen, so I need to see how many moles of SO3 I'm going to produce theoretically. The balanced reaction says for every 3 moles of oxygen, I should produce 2 moles of sulfur trioxide. I have 0.03125 moles of oxygen. How much sulfur trioxide would I end up with? So we're going to solve for x. So 0.03125 times 2 divided by 3. I should end up with 0.0208 moles of SO3. The next thing we need to do is to change moles to grams because my actual yield is in grams. So I know that 1 mole is going to go on bottom, and I calculate the molar mass of sulfur trioxide. The mass of sulfur trioxide is 80 grams per mole. So I multiply that 80 times 0.0208, and theoretically I should end up with 1.664 grams of SO3. So I'm not finished with my problem because what it wants to know is the percent yield. So I'm going to take my actual, which is 1.50 that I had in the lab, divide by my theoretical, which is 1.664, and multiply that answer times 100. So 1.5 divided by 1.664 times 100 is a 90%, which would be a great yield on a test. So in the lab, I actually managed to recover 90% of what I should have, and that's a great percent yield. According to the text, the correct answer is 89.8%, which is the closest one to the answer that we received of 90% yield. The last exercise we're going to look at is this one, and it says what mass of P4 is needed to produce 85 grams of PF3 if the reaction has a 64.9% yield. So let's take a look at this problem. It's a little bit different than the others. So this problem requires a little bit of thinking. This is the actual yield of PF3. That's how much we need to produce. And we know that its percent yield is 64.9%. So what we have to figure out is how much do we need to produce of PF3 in order to get 85 grams of it. So what are we asking ourselves? Well, if we think of it in mathematical terms, what we're saying is what number times 64.9% is 85 grams. And we take 85 divided by 0.649, and what we need to come up with is 130.97 grams, theoretically, because theoretically this is how much we would get, but in actuality this is how much we would get instead, because the percent yield is 64.9%. So this 130.97 grams goes here under the PF3, and what we want to know is how many grams of PF4 are we going to need to produce that much PF3. Let's start with our gram to mole, mole to mole ratio, moles back to grams. So this is in grams, and we want to find this gram over here, so what we're going to have to do is change from grams to moles. The molar mass of PF3 is going to be 87.97 grams per mole. So I have 130.97 grams of PF3. I'm going to multiply that times 1 mole over 87.97 grams. So 130.97 times 1 divided by 87.97 is going to be 1.489 moles of PF3. Now I'm going to go backward. So these arrows, I guess, really should be looking this direction, even though it doesn't really make that much difference. And I'm going to say, okay, if the balanced reaction tells me that P4 to PF3 is a 1:4 ratio. The problem that I have says that I should end up with 1.489 moles of PF3, and I need to know how many moles of PF4 that is. So I take 1.489 divided by 4, and X equals 0.3723 moles of P4. And then you turn around and change that to grams. The mass of P4 is 124 let's back that up. It is 123.88 grams for 1 mole. My moles cancel. So I multiply 0.3723 times 123.88, and my answer is 46.1 grams of P4, which you notice is letter B. So that's the last example that we're going to do. You need to practice, and if you have any questions, just let me know.